Welcome to Cornerstone Home Inspection Education Center. Tonight we have presenter Nick Stone from Rockwool, and he's going to be doing a PowerPoint presentation and tell us all about insulation. I'm going to turn it over to Nick right now.
Hi guys, my name is Nick Stone. I'm the residential architectural specialist for Rockwool. Quick background on me. I spent the last 12 years in the construction space with a heavy focus on wall assembly designs, with everything from interior smart membranes to exterior WRBs to exterior insulation details. And net, with a big part of it being that building science aspect of it. So today we're going to be going over the control layer fundamentals using stone wall insulation, but we're also going to really kind of go at it in the idea of, what is the full wall assembly doing? What are those control layers? How are they interacting with one another? And I'm also going to talk a little bit about some of the different materials that I'm seeing on the market that I think really go well within those layers. Alrighty. Also, if anyone needs to an AIA credit for for whatever reason, this little QR code over here, if you just scan it, it goes right to our Rockwool page, and you can enter your information in, and we can get you credit for that for on the architectural side. But today we're going to be going through understanding control layers. How does temperature affect systems? Insulation ratios, and fire and sound, how they integrate into systems. So just, kind of, starting off big picture stuff, Rockwool insulation really does have avenues through all areas of the building. We have our soundproofing for the interior, for the walls, for our floor systems. We have thermal bats out here on the outside, whether it's exterior wall or in the roof application. We have many different options there now. We do go up to an R38 in that Rockwool for that cavity insulation. So if you're looking for something to meet maybe a overhang, something like that, we have some different options for those areas. We also have our exterior board, the Comfort Board 80. Which is going to be that above grade portion of the wall. That's kind of typically where people think of us, but we're also now designed for that below grade application as well. So if you're looking for somebody who wants a little bit of an alternative to foam insulation, this is kind of a nice option for that. You don't have the leaching of chemicals into the soil. We don't have issues with the bugs, in particular the ants, like some of the foam products. And you can also use this for below slab. We have all of our testing back for a below slab, so it really makes it so you can use a Rockwool product anywhere of the building. The only thing you can't do is put it below that footer. The footer for us does need to go directly to that concrete portion, or sorry, to that to the earth. You can also stucco over Rockwool now for that exposed portion between the soil and the top of the or the bottom plate. That exposed portion, you can now go ahead and stucco over that, so you can kind of make that connection point nice and finished. So we really do have all areas kind of buttoned up within that house. So starting off, what is insulation? What is thermal insulation, I should say? It's a material with low thermal conductivity. Basically, what we're doing is we're reducing the heat transfer from one side to another. Heat always flows from hot to cold. So, depending upon if you're in the winter or the summer, the heat is going to determine which way the drive is going to happen within that wall assembly. So the insulation's responsibility is to stop that drive from one, or at least slow down that drive from one location to another. Taking a look at some of the I would say designs over the years. It used to be We'd have no insulation in our cavity, like you see in this first picture here. That was great when things were, things were cheap. Oil was cheap. We heated with wood, was super common. And then as we, things became more expensive, we started adding insulation into our cavity. Well, we quickly figured out, hey, there's some other things that go along with this. You can't just throw insulation in there. It creates some problems. So then we started looking at that more. And now we're, where we're at today, where we're doing that split insulation, or we have outside insulation and cavity insulation. This is kind of, where that code is now, looking for that 20+5 in most areas, or 13 and 10. And then I think what's going to happen is in the future, we're going to see that we're going to go to all exterior insulation. Cavity only will be service channel for all your wires or plumbing and things like that. I think that this will start to become more and more common as years go on, but we'll see. So this is kind of like just to see the different steps over the years, and see where we've come and how far we've come over those years. The way we build assemblies now, we're really focused on management of the external loads on the building. What I mean by that is you have rain, you have snow, you have temperature, humidity. Oftentimes you have varying humidity, whether it's summer, where it's a different humidity than the winter time. So having the ability to kind of be able to balance both sides of that equation is super important. We have wind, we have UV light, sound, and fire. Factors affecting load management. You also have climate. You have building height, exposure level, usage, interior conditions. This is a big one. So many, it's almost impossible to really figure out what's going to happen long term in these spaces, but that plays a critical role in determining how well these buildings kind of hold up over time. Materials and how they interact with one another, and just overall design of the building. And then you also have, structural loads, gravity, seismic loads, deflection, impacts, and more. So as you can see, as we design and package these wall assemblies or roof assemblies together, it is no longer just what's our thermal design for this. There is a ton of factors that we have to factor in, and each one of them changes that equation just a little bit. So it's important that we think about these systems as a holistic approach when we're designing, or when you guys are out there determining for you guys, what's going in these walls and is that acceptable or not. So starting off with the 4 key control layers, the first one you have to get right is water control. For us, this is really broken down into 2 different things. It's broken down into water shedding surfaces. So that's going to be your outside sheathing out here, or sorry, your outside siding, trim. It can also, if you're using exterior insulation, that's going to encompass that exterior insulation. This is designed to take the bulk water away from the building, keep it out of that cavity location, and get the majority of it away. Then you're going to move into that secondary layer, which is going to be your weather resistant barrier, or WRB. This is going to be, that second line of defense, keeping that bulk water away from the building. This is really the most, it has the most continuity of the 2 options, because oftentimes, they're either stapled down, or even better, they're fully adhered. So they're, completely bonded to the substrate, keeping any water that gets beyond the exterior siding away from that building. Some of the great, WRBs that I'm seeing on the market now, in particular in the fully adhered market, Henry Blueskin VP100, your Grace Envious. There are a bunch of them from Siga and those guys. Or even your mechanically fastened WRBs, like Hydrogap and things like that. Those are all quality WRBs that are going to resist that bulk water from impregnating itself into it and kind of getting into that wood. So that first control layer has to be managing that bulk water. And then we move into our second control layer, which is going to be our air control layer. This is a control layer that gets very mixed up with vapor control. Just understand that air control and vapor control, they are two very different control layers. They can be located at different areas, or they can be located at the same area. Primarily, when it comes to the air control layer, it's happening at the sheathing level. When we start picking, where do we want these to go, in our design and in our building, you really want to look for places to put control layers that have the least amount of, obstacles in the way, that have least amount of ability to have penetrations passing through it. And so for the first control layer, that often happens out here at that sheathing layer. If you're using, products with, like zip, for instance, where you have that membrane put onto the plywood itself, that gives you a great chance to have that continuity very quickly. You tape your seams, or, your fully adhered WRBs or mechanically fastened WRBs. It's very easy to kind of detail those windows and kind of get that air control versus inside. It gets a little more challenging. You certainly can do it on the inside. But when it comes to the inside, you have the electrical boxes, plumbing penetrations, and all those things so much more frequently on the inside, that oftentimes this does become our primary control layer from a air standpoint. But you certainly could detail that if you spend the time to make sure it's correct here on the inboard. The key is that you get to the top of the wall up here. Is you just got to make sure this WRB comes up and over the wall like this and reconnects back into your air control layer on the inside for your sheathing or your sealing location. So reasons why this is super important. Air moves a ton of water, moisture into the assembly. Air moves 15 times more vapor molecules into the system over vapor diffusion through material. It affects the performance of the assembly. So when things get wet, they don't perform well. This is because it needs more energy to dry those materials out. So as it dries that material out, it's reducing the efficiency of that system. So it's super important to get that nice connection, and we can get that nice seal that we're looking for. And also, it's going to compromise your indoor air quality. So this is obviously something important for the end user, and kind of making sure that we're looking at these to maximize the air control. And then moving on to our thermal control layer. So the thermal control layer is trying to resist the heat flow from one area to another. So in zone 5 and 6 in the wintertime, we're going to be warm inside. So it's always trying to drive outward, versus, if it's the flip side and it's summertime, the heat out, the hot air outside is trying to drive inward. So the point of doing the thermal control layer is to resist that heat flow from one side to another. Now, not all areas of the building are created equal. So we have things called thermal bridging, which is a weakness in the assembly. So if you look at the overall wall assembly and you start to look at the makeup of it, wherever there's a framing member, it's a weak point within that wall assembly. Typically, wood is 1 R per inch versus the insulation. Rockwool is about 4.2 Rs per inch. So the insulation is 4 times more effective at stopping heat flow or transfer from one side to another. So by adding exterior insulation onto that package, we're going to slow down that migration through the framing member, whether it's the 2x stud, or whether it's a floor system, whether it's a header. And then we're gonna get that continuity on that outside, so that way we can kind of get that consistency on that thermal migration that we're really looking for on the thermal control layer. And then we get into the also tricky vapor control layer. Now, the vapor control layer in zone 5 and 6, uh, which is the majority of the people on the call here, this is going to be on the inside of our wall assembly, located here at that sheetrock plane. Now, the reasons why this control layer is super important for us is it's going to stop the vapor from the ambient air transferring into the cavity and potentially causing some issues down in the future. We'll get into to the condensation part in a little bit, but when it comes to vapor control layers, it's not all vapor control layers are kind of created equal. Years ago, when you said vapor control layer, the big one that came to mind was obviously a poly. The problem with poly is it's extremely rigid material. So if you were to install poly here on zone 5 and 6 in the wintertime, great. It's going to stop that vapor drive from out to in. But the problem is in the summertime, it actually creates a little bit of an issue for us. The reason for it is now instead of being hot inside, well, now it's hot outside. So now we get a vapor drive from out to in, and it causes some issues with condensation on the backside of the poly, trapping and staying inside of that wall assembly. So now we know that vapor barriers are actually not ideal for zone 5 and 6 anymore. If you go north, you get into zone 7 and 8. Well, those become an option because it's a substantially colder climate for us or for them. But in zone 5 and 6, you really need to get into those smart interior membranes, whether it's a Sigma-Mirex or a CertainTeed membrane. What's nice about that control layer is when it's super dry inside or in the indoor air, it's going to signal for those vapor control layers to keep their cells closed, somewhere around 0.5 perms. And then as it gets moisture inside the cavity, it signals for the cells to open up and dry that system out to the inside through the material, getting that moisture out. And then once it's gotten out of the system and it dries back down, becomes drier again in the cavity, it's going to close those cells back up. So that ability to have that kind of swing within those interior smart membranes are super important for our designs now because of that cooling load that we're adding into these buildings. So if we were to take a look at the perfect wall really wants all the control layers as close as possible to one another. So we want our thermal control layer close to our vapor control, which is close to our air control, which is close to our bulk water management. Ideally, we want them as close as possible so that way we can keep that continuity, whether we're down here at the basement level, whether we're transitioning into our walls or transitioning into our roof. It's really important to keep those kind of in contact with one another. But if you are using, say cavity only insulation or a split insulation, still the big overall arching theme here is that continuity is kind of the king. You really need to make sure as you transition, you're making all those connection points nice and tight for the system. Vapor diffusion in hot and cold climates. So in the heating season, we talked a little bit about this a few minutes ago, but in the heating season, we're going to have the warm, moist interior air. So the vapor drive is going to happen from the inside to the outside, from both a heat driving to the outside, but also from moisture. So wet going to dry as well. So that force is really pushing outward in that winter time. Now in the summertime, it's pushing inward, driving in, which is why those interior smart membranes make a lot of sense within those assemblies. So that's how the climates that vapor drive, that's how those are going to work, whether it's heating or cooling. And that's why when we build these assemblies, we really need to have relief valves built into those equations, if you will, because the different points of the year, they're doing different things. How do you con- how do you control how to control the condensation in your own terms? Basically, there are big three overall arching ways to kind of do this. First, you can elevate the temperature of the critical condensing surface. So, in other words, in the wintertime, if you're heating inside, that first condensing surface is going to be your outside sheathing. Or you can resist the vapor molecules from getting into the cavity. That's going to be your interior smart membranes, reducing how much vapor has the ability to physically get into that system. Or you can remove the moisture from the indoor air mechanically. These are all three different ways that you can reduce the risk of having issues with condensation within those wall assemblies. Another thing to talk about is having a rain screen built into your wall assemblies. So when you have that outward drying, that drying through the system here, pushing that moisture out, having this ability to have a rain screen once it wants to condense, as that moisture dries out, condenses, having an outlet or a drainage plane down here to get that bulk water out of the system is really critical for that design. But also, vapor molecules are lighter than air molecules. So having that ability to, as it comes through and it stays in the vapor form, having an outlet up here at the top is going to give that vapor a release point, getting that, drying that system out, keeping it more effective. Another benefit is by actually having the strapping on that assembly for that rain screen. You're going to provide a 3/4 inch channel, or however thick that channel is. And what's really nice about that is it's going to take the pressure off the siding from a paint aspect. So as if we didn't have this rain screen on here and the siding was directly up against our sheathing here, and that outward the outward drying happened, it condensed on the back side here, and the sun comes up, heats those vapor molecules, it creates a pressure behind that pushing on your paint. So that's going to also go a long way from keeping your paint bonded much better, because it gives that a release or an area where, as it creates a pressure, it can dissipate at the top and dissipate at the bottom, keeping those systems much more effective, the paint on there longer. So having an effective rain screen is also a big part of the equation, things to look out for. In a cavity only insulation system, now we're going to take a look at the dew points and how those look like. We're going to stick to kind of the warm climate over here on this side. So if we have cavity only insulation, so when it comes to dew point, what that really means is once the vapor molecules gets to critical point or 100% relative humidity, the air can no longer hold on to the vapor molecules, and what happens is it turns into a liquid. Now that's only going to happen on the first condensing surface. So when it comes to our dew point, we're going to stick over here in a cold climate. Over here in our cold climate here, as that, the vapor can stay in the air, and then as it gets colder, as it pushes further outward towards the outside sheathing, well, now it can no longer hold that vapor in the air, so it wants to condense, and it condenses out here on the plywood level. So by adding the exterior insulation, what we've done is we have warmed that sheathing up here at this location. So now that the air can hold on to that the vapor, and it doesn't need to turn into a liquid molecule. Where it does out here in the insulation. What's nice about doing it in the Rockwool insulation is we are a drainable material. So we're made with an oil-based binder. So think about how when you're at home in your cooking, how oil and water, how they don't mix, they repel away from one another. That's what's happening once it gets out here to the insulation. It's not absorbing into our fibers. It's letting it drain out, get out the system, get out to the bottom drainage point and out of the assembly completely. There's also no wood out here. So if we think about it from a perspective of wood has mold, mildew, rot problems. So if we can get that moisture out of this cavity and into this insulation out here, well, there's no wood for it to have mold, mildew, or rot problems. So that's going to keep that interior cavity much more durable for the long haul. Oops. If there's moisture in our system and we want it to drain out of the assembly or dry to the inside / outside of the assembly, to help us achieve this, the IRC now has recommendation on the ratios of the exterior insulation to the total insulation R values. Now I'm sure you guys have seen this map here. So when it comes to looking at these ratios, they're broken into zones. We are going to pretty much, for everyone on the call, we're going to be in zone 5 and zone 6 up here. So those all correlate to different ratios of exterior insulation to interior insulation in order to pull our condensation point from our cavity and move it into our exterior insulation out here. So what I mean by that, so if we take a look at zone 5, and for a 2x6 wall cavity, which is pretty typical for us up here, to get that ratio that we're pulling that condensation out, we actually need a total of R27.5 to get that dew point out of that wall system. So in other words, it's an R7.5 on the outside and R20 on the inside. Once you move into zone 6, it gets even higher. We need a total of 31.25, which is going to be an R11.25 on the outside and an R20 in the cavity. So depending, the colder you get, the more exterior insulation you're going to need to balance that assembly out. And this is kind of a big deal because when you start to look at that base code, 20 plus 5 in zone 5 isn't enough exterior insulation to pull that condensation point to the outside of our WRB here. So if you have a vapor open system or a system that allows a vapor to pass to the outside and doesn't stop it, that's okay. But when you start running into some of these vapor closed systems where you have foam on the outside, for instance, that vapor drive can no longer dry to the outside, and we still have condensation forming in here as per base code. So then the question becomes, do we have enough drying potential to the inside to dry that assembly out? Maybe, maybe not. But that's why these ratios really do play a critical role, in these designs, especially as you move into zone 6. Well, that's even higher. That's even further away from the correct ratio to make sure you have no condensation. So having these exterior insulation packages that are not vapor open is definitely something to consider talking to builders about, hey, maybe we should think about some other options because we may have some risk of pulling moisture out of there, drying moisture to that outside, because we may not have enough interior drying potential to really keep that system dry and durable over the long haul. Now that goes the same for your roof assemblies as well. So a roof is a wall is a roof. So if we have our ratios correct between interior insulation and exterior insulation, we're going to take our condensation point and we're going to put it out here in the insulation, giving it a path to dry right out the assembly and keep that system durable. Now, those ratios are a little bit higher than your walls. So if you were to look at an R49 as per base code. If it was a flat ceiling, if it's a slope ceiling, then 20% of that R value has to go out here on the exterior of that sheathing to get that ratio correct to where you won't have any issues of condensation forming in here. So just some food for thought, and kind of when you're talking with your customers, this is definitely more, more of a passive house style design here. You don't see a ton of this, but on your walls, though, that starts to make a lot of sense. That we're looking for a vapor open option to get that release of that moisture out of those cavity and kind of stop that from having issues in the future. So let's take a look at some of the permeances of the material, how much drying potential some of these materials have. So as you can see, the beginning part of this, you have your XPS, your polycyanurate, your paper face polycyanurate, your foil face. All these foams, even your EPS. Once you get over that 2-inch mark, these are all very, much so in that vapor closed category, where they are just not drying through the material. So again, when we go back to those design loads from before, you can see how we don't have enough of that exterior drying potential. So potentially we could create some problems in some of these wall assemblies with our base code. So moving into some of these other options like cellulose, rigid rock wool, your open cell, and your wood fiber, you can see these are much more vapor open material, giving you a chance to dry those assemblies out when it's needed. Moving on to the two other control layers, fire control. When this is something we see a lot more, coming up in play, in particular, where we're starting to build these buildings so much closer and closer together. So having that exterior control layer that has a fire rated control layer on the outside is actually starting to play a big role in a lot of these counties where they're saying, all right, I need a 1-hour wall system protecting that outside. So that way, if my neighbor's house catches on fire or a wildfire or something like that pops up, we're starting to see more and more designs taking place where we need something on that outside to kind of give us that thermal protection. But what's nice about Rockwool is we are made of non-combustible materials. At the end of the day, we are made out of basalt, which is volcanic rock, and then slag, which is a byproduct of the steel industry. So we have extremely high melting points. One of those ways that we test for our melting points is the ASTM E84. And this here, you can see on the upper part here, where we have a 0 flame spread and a 0 smoke development. The way this test works is they basically have a 25-foot tube, and they have insulation line on the bottom. They put a fire or a torch on top, and they just test to see how far the flame travels and how much smoke develops. With that test, we have 0 for both of those. You come down here to the bottom where you can start to look at some of the foam aspects. They have a flame spread of 25, which is the maximum of the test, and a smoke development of 350 to 450. So you can see the kind of the radically different part or spread of the two different insulations from a smoke and flame development standpoint. And then over here on the graph, you can also see our melting temperatures. So the foams of the world, they're going to have a pretty low melting temperature. Your fiberglass has a much more reasonable temperature. But Rockwool really has, it's a 2150 degree Fahrenheit temperature over the course of about 6 hours before anything's going to happen to the material. So when it comes to fire and safety, this is one area that a stone wool material can really excel and make a big difference in connector in those multifamily or areas where there's combustibilities in those rooms or something like that. This is an area that we can really help with that mitigation system. This is a cool little test that we've done to kind of show you a real life example of some of the fire capabilities or resistant capabilities of Rockwool. On the bottom left hand side, this is trying to simulate having a turkey. Having Thanksgiving turkey outside. The turkey gets too close to the house. The siding catches on fire. The bottom one is stone wool or rock wool, and the top one is going to be XVS. It's about a 3-minute long video, and at 3 minutes, take a look at this area up here, and just how quickly that fire and smoke flashes over. Just one other thing to note is the stone or the rock wool is sped up versus the XPS, which is normal time. Now we're starting to get really thick black smoke up here in that EPS.
Nick, while this is playing, what's the easiest way for like a newer inspector who's not familiar with the product to identify the product?
Is compared to other stone walls or in general?
In general. You go up into an attic, you see it. A newer inspector might just look at that and think it's just fiberglass insulation because they're not.
Yeah, so all stone wool material is going to be a dark green in color. It's going to have a lot more density or volume to it than your fiberglass materials. So if you were to grab that rock wool and you were to physically go like this with it, you're going to find that there's a lot of resistance to you almost can't flatten a rock wool material, where a fiberglass, you can almost pancake it flat. So that density factor will be a big indicator of kind of what you're looking for. But green in color is kind of it looks like kind of this color here, kind of that green color there. But it's really going to be that density is going to accept and moisture control. Oftentimes, fiberglass is going to be damp when you grab it or feel it, and it's also going to have a lot of discoloration going through it because it's a very good air filter. So as the air passes through it, it pulls the dirt out of the air. So it's going to be very dirty looking. Rockwool, you just don't really get that because we don't have a lot of air passing through, which is also a great thing because it doesn't pull out the heat energy. So it keeps the thermal value consistent over time. So those would be a handful of really good indicators.
Thank you.
And then moving on to the last part of it, which is going to be the sound, or the SDC, the sound transmission class. Basically, what I wanted to touch on here was just when you're looking at some of these different wall assemblies. I'm not sure how from you guys from a inspection standpoint, what you guys kind of look for on the sound part of it, but just know that when you go in there and look, there are certain things that really jump the categories in performance level. If you have a base wall with just cavity insulation with Rockwool, you'd be looking at an STC of 38. If you were to add resilient channel, that's really going to boost that performance of that wall assembly up to a 47. And if you really have a customer who's really looking for that kind of that top notch, it's getting that double stud wall. That's going to get you that best acoustical performance with something, an STC of about 56. One of the ways to kind of look for from an inspection standpoint, to kind of look out for is continuity. Sound doesn't just travel straight through a material. It's going to travel up and over the material. It's going to try to travel under it. If you have outlets that are stacked back to back, that's actually a really good area for sound to travel through there very, very easily. If you have a mechanical system, it can easily travel up through the mechanical and down through. So just keep in mind, noise is like water. It's going to find the path of least resistance, and it's just going to find it and work its way through. So that consistency factor and making sure they got all those nooks and crannies, just like on the thermal aspect, it also is in the sound aspect of that category too. And if you're looking for that, just as a reference, when you move into that exterior part of it, that exterior insulation also has a sound value to it as well. So we can boost that exterior wall up by 4 to an STC of 39. So there's also some added sound benefit to having that exterior insulation on that wall. Is this something you guys get a lot into? Would this be helpful for me to kind of go through some of these details, some of the things to look out for?
Sorry, my microphone was off. I would say yes.
Okay, perfect. So with the new exterior insulation becoming more and more popular, and also just talking a little bit about the cavity insulation, some of the areas that to kind of look out for, or just in general kind of talk about is starting with the outside. When it comes to exterior insulation, continuity is key, and really making sure you have enough from windows to doors to overhangs. Always having that constant continuity. From transitioning from above grade to below grade, like in here, having that nice control of insulation to here and also down to here. Typically, as you transition from that above grade to the below grade, you're going to have some type of water kick out system here. So that way, water is a positively charged molecule. So as that water rolls down the wall assembly like this, it wants to wrap in down here at that sill plate and suck underneath. So by having that water roll down, having this kick out here is going to force that bulk water away from that building, which is going to save that sill down here at this location. For that below grade application, we always want to make sure we have a waterproofer kind of up against the concrete. We're going to have our comfort board 80 out here at this foundation level. Obviously different codes are going to specify different thicknesses. But one thing to kind of look for is with Rockwool, we can stucco over the Rockwool product on the outside, but it does need a layer of wired lath out here at this location in order to stucco over. So we want to, kind of checking on those items there. When it comes to strapping on these rain screens, I'm a big believer in 3/4 inch strapping is the best thickness to kind of look out for. I've done a lot of different thicknesses to check on, for ventilation, and those work fine. But when it comes to putting on your siding and trim, 3/4 inch is really the minimum that you want to go with. When you go thinner than that, you really tend to have a big tendency to get some waving when you go to put that siding on or that trim on. So 3/4 inch is something I highly recommend from a strapping standpoint. When it comes to fasteners, I'm not sure if you guys get into this or not, but number 9 deck screws, when it comes to exterior insulation, is really kind of that perfect sweet spot of it has enough moment shear strength back here at the sheathing location where it's not going to have issues shearing those fasteners. But it's still but it's still more economical enough to kind of keep the contractors up and moving and everything kind of going. So those number 9 fasteners work out really well for doing exterior insulation. Again, talking about your WRB connection here, as a WRB comes down, making sure we have kind of a transition point from that sheathing to that concrete from an air movement standpoint is super critical. We see a lot more tapes coming onto the market that can go from wall to concrete connections without any primers or anything like that. So making sure that we have that connection point here. I know we have that sill seal, but it's really not quite a long-term solution. Having that connection point here is a much better solution. Both of those do work. Moving to the cavity insulation, we have we have a 5.5 inch, we have a 3.5 inch, depending upon the cavity. So one thing to look for from an install standpoint is you really want to make sure you have continuity of both sides of that install. So when you go ahead to stuff that cavity, put that insulation in, that connection and making sure it's nice and fit from both sides is super important. What's really nice about Rockwool is the ability for it to cut. And I know you guys will appreciate this. When you go to cut a stone fiber, because it's a stiffer fiber, it cuts more at a 90-degree angle. Versus when you go to cut a fiberglass fiber or a sand fiber, it tends to break and pull apart, and it's not as workable as a stone fiber is. So that's why when you go around electrical boxes, plumbing penetrations, it just installs better those areas because of the fiber that it's designed with. So making sure that around these or have all those connection points will be much easier with a Rockwool product. And again, having a vapor control layer here at this location is something that I highly recommend to doing, but not using poly. I really am a big fan of using them with adhesive. So basically my top plates, my bottom plates, my walls, putting a bead of adhesive all around. And then inside my, my framing, putting a dab or a dollop like their nails and taking a J roller and rolling them all in. I'm a huge fan of that. I think it makes a really nice solid system. So you have no fasteners passing into your vapor barrier. You just have so much more continuity that way to really create a very effective system that's not going to allow vapor to kind of pass into that area. Another thing that's really great is if they're putting a service channel. I've seen more and more builders buck this out with like a 2x4 after the fact. So they'll have their control layer on, their insulation in there. So insulation, vapor barrier, they'll buck out a control layer here, and then they'll sheetrock out here in this area. That's super nice too, because we're eliminating any penetrations into that membrane, keeping again that continuity. I know I've said it about 100,000 times, but it's really the key to all these systems. Moving into our box sill here. This is the tricky area for a vapor open product. This is a great product, an area to put foam here at this location. But as we know, protecting that foam is a big deal. So having a Rockwool over that product with our fire resistant capabilities is going to protect that foam from any flames getting to that area. We also have lots of places now with TGIs, you have to protect that flange. Rockwool has a lot of great documentation out here at this TGI location to help protect that flange. Sorry, I should say web. Help you protect that web from fire. So there's some great options for that as well.
Nick, we got a question.
Sure.
Are there classes on how to install these systems for contractors? Do you have to be like an approved contractor? How does that work?
So, so we don't have you don't have to be an approved contractor to install the product. We're actually working right now on trying to put together some kind of install process or a program. That way we can kind of go out there, certify people. But it's just something that takes quite a bit of time. So it's something that we would like to do, and we're certainly working on. But it's as of now, we don't have that process. But we do spend a lot of time. My team does in particular, going out to job sites, showing them, how to do some installs, talking about every installation kind of has a quirk. So just talking about some of the quirks of ours and just making sure they're comfortable with that install, comfortable when they come to a box, know that, hey, we got to cut the box out, but behind the box there's a void. So we got to fill that void in. And then, so that way the continuity is in there. So we kind of go through a lot of those little quirky areas. So that's something, that's we kind of work on every day.
Okay, thank you.
Mm-hmm. So if you were, inspecting a below grade install, this is something that you can see on the outside here. We have our comfort board. We have our waterproofer back here at this location. This is a very common install for us here, where we're coming down to the top of that footing. You can't see it, but this is kind of sitting right on that footing. You can kind of see it right there. If you wanted to go below your slab, you want to go insulation, vapor barrier, and then concrete on top of that. It's really important to have that sequence for a drying standpoint, and also it would just keep that drainage capability always draining, and that's what we want for the Rockwool products. These right here are really great for install applications. So, these are pattern actuated pins. You just basically push them on there, pull the trigger, and you're moving on to the next one. These work out really well. As far as from a holding standpoint, the backfill is really going to be what holds all these panels in place. So no need to go crazy on putting 1,000 pins in this. Just want to make sure there's enough hold, depending upon, how big the sheet is and all that, to have enough time, enough holding power so we can get that backfill in there and get that pressure up against the material, and kind of keep it in place. What's really nice about the Rockwool, because it is so much denser than a lot of other products that are out there. Once it sits on the wall, it just sits on the wall. It doesn't have a lot of movement. The wind doesn't push it around. So it's very durable in that sense. It also doesn't expand and contract. So when it comes to expand and contraction, we expand 1/10 of an inch over 33 feet. To give you a comparison, your polycyanurate is going to move up to 2.4 inches over that same 33 feet. So even though we just stack these, we don't have to tape our seams, because as long as we have continuity of connections, it's not going to expand and contract over time, creating voids and creating some problems behind that. So that density of material staying there in place, you don't have that expansion contraction, makes an excellent material for that below grade where you have these long walls of a possible expansion contraction. So I'm not sure how many of these areas you get into, but cantilever overhangs, certainly in my area, are pretty common. Again, continuities, you're bringing a thermal plane down. We just want to make sure we have our connection point moving on to the other side. Same thing with the air barrier, or our air barrier. As the air barrier comes down, we really want to make sure that it wraps down and around, so that way we don't miss an area here, bringing that continuity around the corner. As we have insulation plane that's a flat ceiling, again, as our WRB, I talked a little bit about this earlier, but as our WRB comes up, we really want to be able to have it connect to the inside, to the air control layer in here. So oftentimes this doesn't happen. So it's good to talk to your framers, before you put your roof trusses on. Get some kind of material, some kind of WRB that's wrapping over this plate. You can staple it down or whatever it may be, and that's going to really help make that connection, continuity connection, much easier for them. When they get to the stage of detailing all that stuff. This is some more pictures of some installs when we were talking about that exterior part, adding insulation on the roof assemblies. when we start looking at the those exterior wall assemblies in the from a window standpoint, typically you got a question of, do I leave my window in like this, or do I pull my window out like this and make a buck system? Leaving your window in keeps it at the sheathing location. So you're just going to tape your window flange to your sheathing area here, which is going to give you great continuity of your air barrier. Then you'll have your exterior extension jamb, which you can see here with this knotty cedar. And then your finishes will go on the outside of that. Or like in this picture, you can pull that window out by bucking that system out. This builder decided to do an insulated buck where he had, in this case, he did plywood 2x4 insulation and then another layer of 2x4 and then connected that all. That's all going to be connected by a tape. So taping from here all the way back down the side and onto the zip panel down here at this location. Continuity at all these locations are super, super critical. So just making sure they all connect is a big deal. And that's it.
We do have one question.
Sure.
Jeff asked, I turned a shed into a workshop recently and was looking to insulate it with Rockwool. Cavity insulate. Do I need anything else on the walls inside? Vapor barrier, sheetrock, or anything?
So you're turning it into a workshop?
Yeah. I think he just wants to put the insulation square on the... Go ahead, Jeff.
Yeah, I just want to insulate it, like in the wintertime, put like a pellet stove out there or something.
So, and are you going to be out there a lot? So, the problem is hypothetically, yes, you want to have some kind of control layer on the inside, because that's immediately going to let that vapor transfer to the outside and condense. But because it's a workshop, you could even just get away with like plywood, just kind of something to kind of make a barrier. My suspicion is you're going to need to tape those seams. That way you kind of have that continuity factor. But for a workshop, I don't see any issues with that, especially being a pellet boiler, because it's pushing off dry heat. And so because of those factors, limited use, dry heat, a reasonable control layer, I don't see why you'd have any issues there. However, if you didn't do something and say that was a normal house, say that's a garage attached to your normal house, because I've seen this quite a bit, where they'll just insulate it, they'll walk away because they're doing other stuff. So years later, they come back to do it. Well, you certainly have a huge potential to have some mold related issues on that sheathing, because every time you turn your car on, you open your doors, whether it's the big garage door or the house door, you're letting a lot of vapor into the assembly. So when it gets colder, it's going to start condensing very quickly and potentially causing some issues.
Okay.
So yeah, I would throw some 7/16 OSB or 3/8, something like that. It's just something thin, and just tape them, and you'll be totally fine.
All right, thanks.
One last question. Cost-wise, how does Rockwool compare to other fiberglass, spray foam?
So when we do a comparison with fiberglass to Rockwool, we say we're about 30% more than fiberglass ish. I mean, obviously it depends upon the market and all that stuff, but yeah, about 30%. But we're gaining a lot more from that 30% as far as water management. Denser material. It holds its R value when things get colder much better. So there's a lot of other benefits to it as compared to foam. We're a little bit less than foam, but we're also talking two premium products, different material, different products in the sense of one's vapor open, one's vapor closed, but they're both very premium products from a durability standpoint. So I would say we're a little bit less than foam, but I'm not sure exactly the number, like a square foot number.
Gotcha. Any other questions? Okay, I think we're good. Listen. Go ahead, Nick. Sorry.
No, I just had a question. What do you guys think of it? Is from is it too much building science? Is it not enough practical application? This is my first real go at having this kind of conversation with inspectors, and I may not have the right info, and I'm just curious for your feedback a little bit, so that way if I do this in the future, I can tailor it more consistently for what you're looking for.
So I think it was an excellent presentation, and it's good for us to know about this, what you presented. As home inspectors, we're probably not going to get into the details with the client as much. Obviously, we can't destroy or move walls or, see into walls and stuff like that.
Mm-hmm.
Where we're seeing insulation a lot of times is in basements, crawl spaces, attics, that kind of stuff where it's visual. At that point, what we're really left to do is look at the condition of it. I think in Connecticut we have to tell where the insulation is, that kind of thing. Stan, do you want to jump in?
Yeah, well, I think the benefit to this is something that we don't see. We're not seeing a whole lot of right now, but I think that for those of us, not me, that have a lot of years left in this profession, you're going to see more and more of it. You're going to be able to identify even if you don't see the insulation because it's in the wall cavity, just the thickness of the wall should tell you what product you have there. Knowing some of the details, you may recognize that something's not installed right, to work optimally, and you don't have to go through every single detail with somebody, but you can say, maybe you want to have somebody that has expertise in this material go over, say, the openings or whatever. They may not be, as you said, the continuity may not be right. So we like to get information, whether we use it or not. It helps us seem a little smarter if we have to talk about it. So I think it was beneficial to me. And I hope everybody else, got something out of it. I may not see one of these for a long time, a house built like this, but when I do, I'll be able to say, hey, that's whatchamacallit.
So it's fair to say, if we do another one of these, concentrate a little bit more on basement, attics, what it is, where it is, sizes, for different applications.
So if I go into a 1960s ranch and I see Rockwool insulation just laying on the floor, is that okay? Or does it need the vapor barrier underneath? Does it need anything on top? Is that a good install?
So those are the type of questions, or you're actually asking me this question?
Yeah. So no. Well, Nick.
Asking.
Yeah. Well, he's asking you. Yeah. But that rock wool that we see in the 1940, 1950 house is not like this.
It's actually not. It's not the same product at all. So that actually is what's called a slag wool. In the mineral wool category, you have slag wool and you have stone wool, and they're pretty different. So when you grab a slag wool bat, it actually is very crumbly, and that's because the slag content is higher. When the stone content is higher, it makes a better, longer fiber. So that way, when you grab it, it doesn't tend to crumble as much on you. So that's why when you grab even some of the new products, they're still made with slag or heavier on the slag content and considered a slag wool. So even the new stuff, when you grab it, can be pretty brittle. So that's a big difference between the 1970s and what we do now, because some of the stuff we produce now is actually almost 100% stone, because we've learned lessons over the years of that stuff doesn't hold up so well. It falls apart a little bit. It doesn't, workability is nowhere near what the new bats are today. So big difference in stone fiber versus a slag fiber.
Gotcha. Okay.
Excuse me. Can I ask a quick question? If you see that slag wool up in an attic of a 1970s, 1940s house, is it still maintaining the insulation value that when it was first installed, or would you recommend that be replaced?
I mean, realistically, it's going to, if you replace it with new stuff, it's going to have a better performance. Now, what's there? Is it performing? Yes. Is it performing at what it was manufactured at however many years ago? My suspicion is probably not.
Okay.
It's probably pretty beat up. Again, continuity. I apologize for saying it so many times, but because it's no longer a square bat like this, it's now kind of doing like one of these things where it's compressed, it's kind of broken down. You're just not holding enough R value there anymore. So by putting a new bat in there that can hold its rigidity over time, it's going to keep that continuity or that consistency of high R value versus kind of what's there is probably degraded, broken down. If it's fiberglass, it 100% was broken
Right.
down and needs to be replaced.
Okay. Thank you. Thank you.
Okay, we're good to go. Thank you very much, Nick. I'm gonna end the webinar now.